Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a great pleasure for me to welcome Professor Edward Lee today at MSR. Edward is a professor and chair at the Department of Electrical Engineering and Computer Sciences at UC Berkeley. He has worked a lot in the areas of embedded software and visual languages and digital signal processing for many, many years. And I think his work, he's had a long-standing interest in concurrency. I think his work is especially relevant today when it seems imminent that we'll have lots of parallel computing hardware, but we don't know how to program it. And he's going to tell us a little bit about it today.
Thank you, Shaz. I wanted to thank you all for braving the fierce Seattle weather to come here today. I understand that icy roads are not that common around here, and so it's a little bit of a challenge. But so the talk that I'm going to give you is actually a variant of one that I gave at Concur, which, as you may know, is the mainstream concurrency theory conference. And you'll probably see that it was actually sort of an odd talk to give at Concur because it's not got a lot of theory in it. But it's really, what I'm trying to do is I'm trying to zero in on the problem of how do we get programmers who are developing mainstream applications to be able to effectively do concurrent programming. And I think we've got some pretty big challenges facing us in this dimension, as I'll outline. So I think that software practice as of 2007 in concurrency, I think, tends to divide along religious lines. There's kind of the shared memory model view of the world, which is principally threads. And then there's the message passing view of the world. And I think it's unfortunate, but a reality that although there's been a lot of work in concurrent models that don't fall into either of these two categories quite so cleanly, that those have really stayed out of the mainstream, fairly effectively stayed out of the mainstream. And I think that that's a bit of a problem. But I think there is really actually a rich, in fact, a motherlode of results that date back to the 1960s that we can draw upon that, you know, given where we are today with the technology, some of these ideas that have been around for some time may be worth resurrecting. So you all know the buzz, of course, which is that multi-core architectures will finally bring parallel computing into the mainstream. And that in order to effectively exploit them, we need legions of programmers to emphasize concurrency. In fact, I started working on this talk when we got visitors at Berkeley from Intel and from Sun Microsystems and from HP who were hounding us, really, I mean, in a fairly heavy-handed way, to modify our programming classes in our computer science curriculum to introduce a lot more multi-threading into these programming classes. So they really wanted us to teach programmers right from the beginning to write multi-threaded code. And some of us were not that happy about doing this, and I was perhaps on the extreme of this because, frankly, I feel that there's some fairly fundamental flaws in that technology. And the picture that I'd like to present is that actually, if Intel was successful in convincing us to train legions of programmers to write multi-threaded code, and those programmers go out in the world and write the next generation of applications, that there is real risk that the next generation of processors, the multi-core processors that run those applications, will become known as the ones on which most programs crash. The argument really is that one interesting thing about multi-core architectures is that they expose a great deal more interleavings of multi-threaded code than you see normally in single processor executions of the same code. My belief is that most multi-threaded code is riddled with concurrency bugs, and those bugs don't show up often for years because you actually get relatively few of the possible interleavings in the execution of that code. So the vendor push, I think, is actually potentially damaging to the vendors. Okay? So I've given you my view of the answer to this question. Is this a good idea? I think no, it's not a good idea. We should not, in fact, send out legions of programmers to do multi-threaded programming. My claim, in fact, I'll put it right up front, and this is the claim that I'm going to try to defend, is that non-trivial software that's written using threads, which principally use semaphores and mutexes as a synchronization mechanism, that such code is actually incomprehensible to humans. Okay? So the point here is, this is a pretty strong statement, and when I started, I started working with multi-threaded code about 15 years ago in C++, using what at the time were pretty non-standard thread packages. This was before POSIX, and so the threading packages that were out there weren't standardized. They were all incompatible, had different approaches. I switched to Java a little bit later, and throughout the first 10 years of working on software of this kind, I thought it was a failing of me individually that I couldn't understand these programs. And I've come to the conclusion that it's not just a personal failing, that these programs are actually incomprehensible. Okay? So I'm making a very strong statement, and I'm now going to try to defend it. Okay? So I'm going to defend it first with a simple example. And this is a simple example that's drawn from the famous Gang of Four book on design patterns. Okay? So many of you have probably seen this book. It has essentially a catalog of a bunch of very commonly used design patterns in object-oriented software. And one of the very first patterns and one of the very simplest patterns in the book is the so-called observer pattern. And this is a direct quote from this book, okay, which describes what it is, but it talks about a one-to-many dependency between a subject-object and any number of observer objects, so that when the subject-object changes state, all of its observer objects are notified and updated automatically. Okay? So you've got an object here. When its state changes, a bunch of observers get notified of that state change. Very simple pattern, extremely common pattern, used, for example, in model view controller design of user interfaces. It's a very common way to do that, right? If you've got a bunch of views, a model of some data, the data gets modified, the views get notified. They update their rendition on the screen, for example, of that data. That's a common application of this design pattern. All right, so let's, I apologize for using Java. I understand here Java is a four-letter word, but it's what I use, so I'll use it as my programming language for these purposes. But in Java, it's very common to implement this observer pattern. And the typical way you do it is you have some method in an object that changes the state of the object. So in this particular case, we have a set value method that takes an argument that's the new value for that state. And it updates the state. So my value here is a private variable for this object. And then it proceeds to notify the listeners, where the listeners are simply a list of listeners that are maintained. And there's a method that adds listeners to that list. Okay? You see this all the time in Java programs. Now, this particular piece of code is actually not thread safe, because it might be possible while you're in the middle of executing this set value method for some other thread to call the add listener method and modify this list while you're iterating through that list. So that's a problem. So you need to address, if you're going to have multiple threads accessing these methods, you need to address this problem somehow. So one way to do that is simply to use the synchronized keyword in Java. Okay, the synchronized keyword in Java implements the Java style of mutexes. And all this does is set essentially a lock associated with this object that prevents any two threads from being in this method or this method simultaneously. Okay, so what will happen is if any thread attempts to call set value while some other thread holds the lock, then that thread simply stalls, until the lock is released, at which point that thread continues and proceeds with its method call and acquires the lock and then executes the body of the method. Now, this synchronized use of these synchronized keywords will actually, in a sense, make this code thread safe because it prevents this problem of simultaneous modification of the listener list while you're iterating through the listener list. But actually, if you go to the JavaSoft website, there's an extensive discussion forum there for coding styles, and they actually recommend against this solution to this problem. Okay, and I guess I would ask you, can you maybe someone here could comment why this might not be such a good solution to this problem? I'm sure many of you have faced this problem before, right, of having to implement thread-safe listener patterns, and so you.
There's a scalability performance problem where if value change takes a long time, then you block all the callers to add listener or other callers to add value.
Yeah, there could be a performance problem because you're holding a lock on this object while you're calling value changed. Okay, but there's actually a more fundamental problem, which is that value changed is sort of it's an arbitrary external method belonging to some other object, and you're not really sure what it's going to do, right? And one of the things that it might do is attempt to acquire a lock on some other object, right? Okay, and it could stall. So actually, it's worse than a performance problem because value changed might not return, in fact, because it might block acquiring a lock, okay? And in particular, the owner of that lock, which is another thread, okay, may, while holding that lock, call, for example, add listener and block. And then you get a deadlock. Now, you could say, well, that's sort of unlikely to occur. Value changed. Is it really going to acquire locks on other objects? Maybe it won't happen. Let's not worry about it. Let's just wing it and do it. Okay? Okay, so let's do it, and we might get away with it. In fact, I have direct experience with this. There was one time when in my group we were doing a code review of some Java code that was part of the Ptolemy project. This is a particularly well-attended code review, but this was sort of what we did with these code reviews. We would get around the table, everyone with laptops open, go over line by line pieces of code, and in fact, a lot of the focus of this was, in fact, on rooting out concurrency problems in the code. And in one of these code reviews, we actually identified a method, which if you can read it from the back of the room, I don't know if you can, but this says add change listener. It's actually an add listener method, so it's exactly this pattern. And we determined that, in fact, this method was being called by multiple threads, and there was no mutual exclusion implemented. Nobody had seen any problems, right? So we had a race condition that could have led to a concurrent modification exception in execution, but never did, right? It just didn't show up. But nonetheless, in the code review, we identified a flaw in the design. So we used this solution that JavaSoft recommended against. We synchronized the appropriate methods. 3 days later, we get an email message from someone in Germany saying, I'm seeing this funny deadlock that I've never seen before. Here's a stack trace of the threads that we're executing, and sure enough, it was exactly this flaw that was exhibited, that in fact the notification method was in fact acquiring another lock, and we were getting this deadlock condition. So it does happen, in fact, even with this pattern. So it's not a particularly good design. So we can try to improve on the design. So one way to improve on the design would be to do the notification outside of the synchronized block. This also addresses the performance problem, right? Because we're not going to hold the lock while we do the notification. But there we have a risk because, of course, the list of listeners, now we have to ensure that that list doesn't get changed while we're doing the notification. Okay, so a simple strategy is we copy the list of listeners while we're in the synchronized block. Okay, we create a new data object for which the only reference to it is local to this scope. Consequently, it's impossible for anybody else to have a reference, any other thread to have a reference to this object, so no other object can modify that list while we're using it. Okay, so it's going to be safe to use this list. We know it's not going to get modified. We drop out of the synchronized block and we do the notification. Okay, seems to solve the problem, and in fact it does prevent deadlocks. But this code is still wrong. Okay, and I'll challenge you again to think about what's wrong with this code.
The new listener didn't get updated.
The what?
If during because you clone the listener list,
Right.
So if there is new listener get added to this list during this updation.
Yes, that's true. If a new listener gets added to this list during the notification, that new listener will not be notified of this particular update. That's an intrinsic race condition that's actually a property of this design pattern. Okay. And I think that race condition is actually probably acceptable. It's a sort of a semantics question of whether it's acceptable or not. Okay? But my guess is it's probably acceptable in this case. Okay, so that's actually not the problem that I was addressing. It might not be acceptable, but that's but that's not the flaw that I was addressing. Any other ideas?
What if someone removes a listener?
I'm sorry?
What if someone removes a listener? Is that possible?
Yes, you can remove listeners. I've sort of deliberately left that out of this pattern. So, yeah, that would create another host of problems, potentially. It's actually a very subtle problem, right? Suppose you have two distinct threads that call set value, okay? Because the state of this object changes within a synchronized block, one of those threads will execute first, change the state of the object, then release the lock. Then the other thread will execute, change the state of the object again, and then release the lock. Okay? But now the listeners may get notified of those value changes in the opposite order. Okay? The thread scheduler allows for that. It could happen. All right? As a consequence, think of the model view controller example. Suppose I've got a model view controller and I have two graphical renditions of the state of this object. Okay? I could get two different renditions because these two graphical renditions would have concluded that the final state of the object was different. These would be two inconsistent views of the same object simultaneously on the screen, confusing the heck out of your users. How can this be? You know, this one says that the state is this one says that the state is that. What is the state? Okay? Notice that this is a semantics error now. Okay? And it will never show up in testing. Okay? At least not in any formal way. This does not show up as deadlock, something that's easy to detect when it happens, right? In fact, it doesn't show up as anything that's easy to detect. How would you even construct a test for this? Okay. Very subtle semantic error in code that otherwise looks okay. Now, I'm not going to solve the problem for you of how to implement the observer pattern in Java. It can be done. Although people have told me, who have heard me give this example, that it's kept them awake at night for several days after my talk to find a good way to do it. Okay? It's actually sort of amazingly difficult to do it right. This is a problem. Okay? And this is the simplest, one of the simplest design patterns in the Gang of Four book. Right? The design patterns get more elaborate even in that book, and that book's only dealing with simple design patterns. What if you have more elaborate design patterns? So I have another story from our own software development that had actually a fairly elaborate use of concurrency. It was actually a technique that was allowing for modification of a program while the program was executing. Okay? So you could interactively change the structure of a program while the program ran, and we wanted to do this in a semantically clean way. So we had to manage the concurrency very carefully there. We had code that we put a lot of effort into to get that management of that concurrency right. Okay? And we had people who were pretty smart, had a lot of experience with concurrent software working on this. We did design reviews of that code. We did code reviews of that code. We wrote regression tests. We applied metrics to these regression tests that showed that we were getting 100% code coverage. Every path that you could every flow control path that you could go through that code was actually getting exercised. We ran those regression tests in a nightly build on a 2-processor SMP machine, which would expose different interleavings in the thread scheduler than what the development machines were using, which were all single-processor machines. And that code got used by every user of the software every time they used the software. And it took 4 years for a deadlock to show up under all of those circumstances. Okay? 4 years later, I remember the date because I was giving a demo to one of our sponsors. Okay? And the system deadlocked on me, and I had the presence of mind to capture the stack trace before recovering and restarting the demo. Okay? If it takes 4 years for a concurrency bug to show up, okay, and this is a concurrency bug that's detectable, okay, it took it 4 years to show up. What about the concurrency bugs like the previous one that I gave that are actually not detectable because they may or may not be semantically correct? Okay?
And it only showed up when it was most embarrassing?
It only showed up when it was most embarrassing. In fact, that's probably, the best code testing technique is find the most important person you can find and show them your code. Okay? Yeah, Murphy's Law has something to say about this. But my contention is that, you can't trust this software, right? And every time I use the synchronized keyword in Java, I get dread, frankly, dread, okay? It really makes me nervous. I puzzle over it for hours. Can I use the synchronized keyword here? What are the consequences of using the synchronized keyword here? Okay? There are people, I think, who know how to use it reliably. Doug Lee, for example, is probably one of those. There's very few people in the world that I would trust, actually, though, to use it correctly. And yet, Java programmers are using it all the time. Okay? This is a problem. So maybe concurrency is just hard. And there are people who have argued this point very eloquently and I think quite appropriately. One of them is right here, for example, Jim. This is a quote from one of his papers in ACMQ. Humans are quickly overwhelmed by concurrency and find it much more difficult to reason about concurrent than sequential code. Even careful people miss possible interleavings among even simple collections of partially ordered operations. I completely agree with the second sentence, but not the first. Okay? Because I think that concurrency is not the same thing as interleavings. Okay? In fact, the interleavings are a way of realizing concurrency, and they're a conceptual model that we've built into this threading model. Okay? But they're not the only one. And in fact, I can argue that humans are actually quite adept at dealing with concurrency, and that in fact, if we weren't, we would have a very hard time functioning in the physical world. Driving your car, for example. In a sense, you are instinctively reasoning about concurrent actions around you all the time, and in fact, it's essential that you do that effectively in order to drive your car safely. Okay? So I don't think concurrency may be hard, but I don't think that's the essence of the problem. I think it is possible for humans to reason about concurrent processes. I think it's threads that are hard. Okay? Threads are sequential processes that share memory. Okay? From the perspective of any one thread, the entire state of the universe can change between any two atomic actions. By the way, even the notion of an atomic action can be really problematic. There's a whole string of papers by very smart people arguing about the Java memory model. Okay? It boggles the mind how much can be said about a two-line program. Okay? Two-line program. A string of papers arguing about what it means. Okay? And it boils down to, what the heck is an atomic action really? Okay? So that problem in and of itself is difficult. But this is even worse, right? That from the perspective of any thread, the entire state of the universe can change between any two atomic actions. So if that happened in the physical world, right, then from one instant to the next, I might find myself talking to an empty audience. Okay? Well, that could happen anyway. You guys might get fed up and walk out on me. But but I'd see you walking out, actually, so I'd be able to observe the state transition, right? If from one instant to the next the state of my universe changes, something's wrong with my physical world, okay? So the problem is that we have a concurrency model in software that doesn't match what the physical world does at all, right? No observer in the physical world sees the physical world operating that way. The states don't change in some hidden way from one instant to the next. So we need concurrency models that are more like the physical world, right? This one is pretty far from what the physical world does. And consequently, it's not that surprising that we would have difficulty reasoning about it. So there are partial solutions, right? One is training programmers to use threads. So if you go, for example, to someplace in Pittsburgh and ask them what the solution to this problem is, well, it's we need better software engineering processes, and we need everyone to be up to level 5 CMM, and we need proper processes in place. Yeah. It's the real problem is programmers are lazy, and we need to whip them into shape. Well, yeah, it's probably true that programmers are lazy, but I think, and I'm sure that you can help things with better software engineering processes, but does it solve the problem? Not if the programs are fundamentally incomprehensible, okay? That's my contention, is that if the programs are fundamentally incomprehensible, it doesn't matter how diligent the programmers are. They're still not going to understand their programs, okay? And I think understanding your program is the surest way to get it to work, right? So we can do things like, it's very, very popular to devote attention to non-functional properties or use design patterns. These are Band-Aids, I think. And they're Band-Aids that are trying to address a fundamental problem in the foundations. Now, we can make other improvements. So there are, in fact, techniques that are actually quite effective at making the situation much better than the way I portrayed it. So the fact is, if you're writing a multi-threaded Java program, your universe doesn't change in completely uncontrolled ways out from under you. Why? Well, because you use object-oriented design. And there are portions of your universe that have very limited visibility. So not every thread can get access to a reference to these objects that are part of what you consider to be your essential state. So you carefully regulate which parts of the program have access to which parts of data, and that does contain the problem. It helps, actually, I think, an enormous amount. You can try applying coding rules. So, for example, Doug Lee argues for this standard pattern. If you're going to acquire multiple locks, always acquire them in the same order. That's actually pretty hard to do in Java, in part because it's not part of the interface of a class definition what locks a method acquires. So you don't actually know until you look at the source code, and the source code called by that source code, what locks are acquired by a particular method call. So the interface information isn't there to apply this rule, okay? But even if you could fix that problem and augment the interfaces so that you could apply this rule, it turns out it's often a pretty difficult rule to apply because, for one thing, it prevents you from being able to do completely symmetric accesses to objects where you're not sure where the access is going to originate. You can use libraries. So libraries are, basically you rely on somebody else, some concurrency guru to have gotten it right, and that helps a lot. You can use patterns that have vetted techniques. So for example, MapReduce is a very nice pattern for highly concurrent software. It was developed at Google. Transactions are an enormous help to this problem because they fairly dramatically reduce the number of relevant interleavings of the software. These things all actually help in major ways. Formal verification can also be an enormous help. So for example, the deadlock problem that took 4 years to show up probably could have been detected by formal analysis of the software. However, the subtle condition about the notification happening in the opposite order, I wouldn't even know how to specify that, the verification question. So it's unclear to me that one could have been identified by formal verification techniques. There's a lot of very interesting work in enhanced languages that have cleaner concurrency models. Guava, for example, is a variant of Java that comes out of IBM that I really like. It has a very, very much more understandable model. But somehow all of these are troubling to me because I feel like we're ultimately building on a flawed foundation, okay? And the reason that I believe that it's a flawed foundation is that threads are actually wildly non-deterministic, okay? Arbitrary interleavings of atomic actions are theoretically possible, okay? And the programmers are asked to rein in that non-determinism by using techniques like these, okay? You prune away the possible interleavings using these sorts of techniques. But is that a good engineering design principle? You know, think about it. If you, suppose I were to ask you to, suppose you're a mechanical engineer, and I'm going to ask you to design an internal combustion engine. And I'm going to give you a big vat of hydrocarbon and iron molecules all swimming around in this vat. And I ask you to constrain the motion of those molecules until you get an internal combustion engine. Is that a good way to approach the design problem? Well, no, probably not, right? Yet I think that's what we're doing with threads. We're taking something that is wildly non-deterministic and we're asking the designer to prune away non-determinism until they get the behavior they want. I don't think that's a good design principle. In fact, I would argue that if the foundation is bad, then we're going to get brittleness in designs regardless of how many of these patches we put onto the design principles, okay? This, by the way, one time when I used this analogy, someone in the audience pointed out, raised their hand and said, you know, people have made a lot of money off of that particular piece of flawed engineering. And then he suddenly realized, it's a perfect analogy. He realized that. I didn't have to tell him. By the way, I should point out that this whole thing is held up by threads. You can sort of see them in the picture there. So I actually really question this fundamentals of this approach to concurrent software. I think that this is really not the way we want to be going ultimately. So the succinct problem statement is that threads are wildly non-deterministic, and the programmer's job is to prune away this non-determinism. By the way, why is it that despite this fact that threads are so popular as a programming technique? And I think the reason is actually very simple, which is that if you start with imperative programs, introducing threading has one very nice feature. It doesn't change the syntax. Syntax is almost completely unchanged. Okay? In Java, all you do is add the synchronize keyword, and other than that, there's nothing in the syntax that changes when you go to multi-threading. Programmers, unfortunately, seem more governed by syntax than by semantics, right? They're much more reluctant to use a new syntax than they are to use a new semantics. And I think that's part of the appeal of threads, is that you can jump from sequential programming to concurrent programming without learning new syntax. Never mind that your whole semantic foundation is gone, okay? But it does make it appealing. So what is the solution? Well, I think that we need to apply this basic engineering principle. Instead of starting with a wildly non-deterministic mechanism and asking programmers to rein in that non-determinism, we should start with a deterministic mechanism and incrementally add non-determinism where we need it. Seems obvious, okay? But how do you apply this to concurrent software? Well, unfortunately, under this principle, most of today's techniques, object-oriented design, transactions, message passing, they all require fundamental rethinking, okay? So what should that rethinking be? Well, let me first address this semantics question, okay? I'm going to summarize the 20th century for you, okay, in 2 slides. So the 20th century, at least from the perspective of computation, right? What is computation? Well, if I define the set B as a set of bits, it's just got two elements, 0 and 1. Then I can define the set of all sequences of bits, okay? And now a computation is simply a function that, given a sequence of bits, gives me another sequence of bits, okay? I can compose computations by simply doing function composition. In fact, this is one of the most effective abstractions in software, which is procedures. Okay? Procedures compose by composing these transformations of bits. Okay? And formally, it's just function composition. So programs, in fact, just specify compositions of computations without threads. Okay? The problem is, when you add threads, this doesn't really work anymore. Okay? And let me show this to you in pictures. So if we think of a program as starting with some sequence of bits, that's the current state of the machine when the program starts, okay, plus all the inputs to the program represented in that sequence of bits. Then the program simply executes a bunch of procedures, each of which is a function that transforms the pattern of bits into a new pattern of bits, until you get to some final state, at which point you declare yourself done, and that's the output of your function. But if you're within a multi-threading context, between any two of these function applications in a program, some other thread may intervene and change that bit pattern out from under you. Okay? As a consequence, now, when you compose procedures, it's no longer function composition. In fact, procedures are not functions anymore. Okay? We've actually lost one of the most fundamental appealing properties of computation, okay, which is that procedures are functions that transform bits. We've lost that. And we can't compose software components by composing functions. That's a really fundamental problem. So programs as mappings from bit patterns to bit patterns is not going to be a rich enough foundation for computation. Okay? What should we do instead? Well, I think we need to enrich the foundation. Okay? So in particular, I think programs should be functions so that we can compose them in semantically clean ways. Okay? We want them to be functions. But their inputs should not be simple bit patterns, but rather evolving bit patterns. Okay? So the input to a program is going to itself be a function. Ignore the superscript here, okay? But the input to the program might be a function that maps, for example, time into bit patterns. Okay? Now the input to your program isn't a bit pattern fixed, but an evolving bit pattern in time. Okay? The output of the program is also an evolving bit pattern in time. Now, if you think about it, this is actually what most programs do, right? They do deal with evolving bit patterns. They don't get presented with all their input right at the beginning. They, acquire input while they're executing, for example, and they produce output incrementally. But the foundations of computing don't reflect that, right? Because they model programs as functions that map bit patterns into bit patterns. So I think we need this richer model. These superscripts are just allowing for the possibility that a program may have multiple inputs, multiple evolving bit patterns coming in, multiple evolving bit patterns going out. Okay? But now, if programs are this, I can now compose programs concurrently, and it's still function composition. Okay? Because I can take the output of one program, which is a bit pattern evolving in time, and feed it as the input to another program, which takes input as a bit pattern evolving in time. And I can think of those two programs as executing simultaneously, and in fact, I can execute them simultaneously. But their composition is still function composition. So I've preserved the fundamental property of being able to compose programs in a semantically clean way. Okay. So let me give you a concrete example of what this might look like and what the implications might be. So this is a very, very simple example. Okay? This is a process network that's constructed using the particular style of Gilles Kahn, which is simply a design pattern. You can think of it as a design pattern for message passing systems that happens to preserve determinacy. So programs will always execute the same way concurrently if they're specified as Conn process networks. So the way these process networks work is you can think of each of these as a program, but it has its own thread of control. Okay? So program P and program Q execute simultaneously. And they read inputs from input ports. So Z and U are input ports to P. And they write outputs to output ports, V. Okay? P writes output ports, the program P writes outputs that will at some time later get read by the program Q, okay, which will then produce outputs that will be later read by the program P. Okay? So you can have these concurrent programs. Each program can be specified now as a function, but interestingly, it's a function that maps an entire sequence of input values to an entire sequence of output values. Okay? The presence of a feedback path here suggests an interesting semantics question, right? What does it mean to have a feedback path like this if the program is a mapping from an entire sequence to an entire sequence? It's a resolvable problem, actually. You can give this a fixed point semantics, which is simply that the sequence that is fed back has to be a sequence such that if that sequence is given as an input to this function, the resulting output sequence then given to this function produces this same sequence. So the meaning of the program will simply be whatever sequence satisfies that property. Okay? So formally, what does this look like? Well, P is a function, Q is a function. You compose these two functions. The meaning of these sequences is a fixed point. It's a sequence that satisfies both functions. Okay? In terms of this view of the program as mapping evolving bit patterns to evolving bit patterns, you can actually formally structure this thing very carefully and actually do some pretty nice static analysis on it. So in the terminology of Gilles Conn, this program was called a process. By the way, this was done in the early 1970s, okay? And, it's a familiar realization of a simple special case of this is Unix pipes. Okay? Unix pipes don't support feedback, but they basically support this kind of asynchronous message passing with blocking reads. Okay? If you augment them with the ability to support feedbacks, you get Conn process networks. Also an interesting anecdote, I mean, in the Unix world, people were writing concurrent programs way back in the 70s. And the way to write concurrent programs was using processes, not threads. Threads were the domain of operating system experts. Threads were what the device driver guys had to worry about. It wasn't until the 90s that threads got exposed to programmers as a programming model. And I believe that will end soon, and we will start to view threads as a big historical mistake. They never should have been exposed to programmers as a programming model, and they'll be replaced with the next thing. But
why did that happen, Edward? I mean, they could have added processes just as easily without changing the syntax, right? If the only advantage of threads is that you don't have to change the syntax, then it could have been done with processes.
That's true. I think it was an inexorable drive towards expressiveness and generality. Right? There's sort of an axiom in computer science that if something is more general than something else, it's better. Right? You can implement processes with threads, but not vice versa. Therefore, threads are better than processes. Right? Well, maybe not. Right? I mean, expressiveness can come at a cost as well. Right? So I think that it's what made it happen was this inexorable drive towards expressiveness. So the interesting thing here is that if I view, if I view the signal coming into Q as a function, so this set T is some tag set. In particular, it could be time, it could represent time. So the input might be a time evolving bit pattern, but it doesn't have to represent time. It could be something more abstract. It could be partial order, a partial order representation of time, for example. And in particular, in the case of Conn process networks, the appropriate model is a partially ordered model of time because these processes do execute highly asynchronously. So if I use a partially ordered model of time, I can get a partial order structure that relates all of the data values that are exchanged between these processes. So if P sends a message to Q, okay, that message will be represented by a dot along, V right here, this signal V. So this is a message sent by P. This is another message sent by P. These messages are ordered. The second message sent by P is sent after the first message sent by P. Okay? This is a message received by Q. It is received after that same message was sent by P. Okay, so these lines represent an ordering relationship between these messages as viewed by the processes. All right, so the interconnection between processes describes a partial order structure on these messages. The processes themselves also may describe a partial order structure. So in particular, suppose that P is described as follows. P just reads from an input from Z. If there isn't anything there, it'll block until there is something there. Okay? Then it reads something from U, and then it produces something on V. Okay, so and then it just repeats that forever. Similarly, Q will just read from X and write to Y. Okay? These programs themselves also imply an ordering relationship on these messages. And in fact, if I superimpose this ordering relationship with the previous ordering relationship, this one, I find that they're actually inconsistent. Okay? Which exposes the fact that this particular program will deadlock. Okay? So you can use this structure, this mathematical structure, the function composition. By the way, the function composition semantics still works perfectly well. This program is well defined. Okay? It just so happens that the meaning of the sequence on this feedback path is the empty sequence. Okay? And that's in fact well defined by the program. Okay, so this is sort of a hint at this idea that you can in fact build a theory of computation here that has nice mathematical properties, that leverages function composition and is highly concurrent. Okay, that's the key point. You don't have to give up on the function behavior of software in order to get concurrency. Okay, that's really the message that I'm giving by giving a hint to this formalism. I'll skip over the timed example, but let me get to the catch now. So the problem is that I'm suggesting that programs be viewed not as something that takes an input bit pattern and gives me a new input, an output bit pattern, but rather as something that reads evolving bit patterns and produces evolving bit patterns. The problem is this is not what mainstream programming languages do. Okay? That's not what a Java program or a C# program expresses, at least not directly. Okay? And it's not what mainstream software component technologies do. In particular, object-oriented design does not do this. Objects are not these kinds of components. An object is not something that reads an evolving bit pattern and produces an evolving bit pattern. Okay? So what should we do? Well, let me tackle the second problem first, okay, which is the component technologies, because what I'm going to claim is that if we solve the second problem, we actually don't have to solve the first problem. Okay? Yeah.
But there is also an issue about, I mean, this is perhaps the same thing, expressiveness, right?
Yes.
Okay, sorry.
Well, that's right. Absolutely. There's expressiveness questions in here, and in fact, one thing that I would point out is that there's a lot of different variants of this that influence the structure of these sets. For example, whether they're partially ordered or totally ordered, and so on. There's lots of concurrency models that actually fit this pattern. Okay, and there's been enormous debates going back to the 1960s again about relative strengths and weaknesses of this. Many of them centering on expressiveness questions.
So, I have a
Yeah.
question. Do you think that by having this new kind of semantic model, many errors would be eliminated? It seems that we are not able to eliminate deadlock at least, right? We can still write programs at deadlock, and it will again be difficult to check them statically in a precise manner.
That's true in the sense that in the case, for example, of con-process networks, you can write programs that deadlock, and the deadlock question is going to be still undecidable.
Yes.
Right? Any sufficiently expressive language will lead to an undecidable deadlock question. Right? Sort of has to fundamentally. That's absolutely true. I think that the key benefit here, it doesn't come principally from the ability to do formal analysis. It comes from the ability for humans to understand these programs.
I see.
Okay? And so the analogy that I would draw is that this is much more like the physical world. Objects in the physical world coexist and interact. Right? Objects in software don't do that at all. Right? They're just bundles of data that, sort of somebody reaches in, some sequential thread reaches in and changes the state of the object. It's actually hard to even construct a physical analogy to this. The physical world doesn't work that way. The state of objects doesn't change that way, right? So this, I think, programs constructed like this are much easier to understand. I'll give a simple example later on in which I can show you, I can prove that an implementation of the observer pattern that uses this style is free of deadlock by inspection, right? Just look at the source code of the program and say, yeah, there's no deadlock here. Okay, I'll show you that in a minute. We don't even have to do any formal analysis. Okay, so let's talk about the component technology. So the problem that I have here is that object-oriented design. Now let me make it clear that I believe object-oriented design was an enormous increment in capability in software. Absolutely wonderful thing, right? Enabled us to scale up programs very dramatically compared to what we could before, because it enabled us to talk about the structure of software at a coarser granularity than the ways we were talking about it before. However, it doesn't address concurrency, okay? And the question is, how do we address concurrency? So in object-oriented design, at least as realized in today's prevailing object-oriented languages, which is C#, Java, and C++, an object is a bundle of data and methods, and the way you interact with it is by a sequential thread calling a method and getting a return value. You reach in, do a state transformation, get out. Okay? The alternative is what I call actor-oriented, okay, which is a component that also has state. It has data. It's a bundle of data, okay? But instead of call return, data flows through that component, okay? It's just, it's a simple twist. And in fact, this is easy to implement in an object-oriented language, okay? So they're not, in fact, incompatible in any way, right? But it is a different way to think about the component structure of software. Components like this are going to be intrinsically concurrent, okay? And they're going to have much better analogies to the physical world, because this is what objects do in the physical world. They react to stimulus more or less continually, and they produce stimulus more or less continually, okay? So what flows through an object is evolving data rather than sequential control. Yes, a question?
This input data which is flowing through the object, this flow is somehow discrete, right?
Yes.
So this is a sequence of readings, right? Therefore, what is the fundamental difference between call and the action of reading?
Actually, there's quite a lot of difference, right? Because this object could, for example, have its own thread of control, okay? Sequentially, perhaps reading its inputs. That's not the same as something where the sequencing is entirely determined externally to the object. This component has no control over the sequence of actions. This component does, okay? So it really is, in some ways the differences are not that big, because in fact you can find object-oriented programs that are actually using this style, okay? But they weren't thinking of it that way. Yeah.
Good question. So, supposing you had an actor and two other actors simultaneously wanted to talk to that actor,
Mm-hmm.
are they going to have to communicate with a single pipe, or there will be as many pipes coming into that actor as the number of actors wishing to communicate with it?
So one
I
key...
think that is a fundamental difference between the threading model and this one, right?
Yeah, but one key point that I would make is that there's actually many possible semantics that one could associate with the interactions between actors. Okay, I think actually this view of components breaks open the whole programming languages world and begs the question of what are the languages that we want and what are the semantics of those languages. So one example would be con process networks, right, which says that this has a thread of control. It could have two input ports, but it must read them sequentially. Reads from one. If there's no data there, it blocks until there is data. Then it reads from the other one. Okay? That's a constraint that's imposed by the choice of doing con process network. Another possibility would be a CSP style interaction, which says that if you have two input ports, that I actually might insist on reading from both of them at the same time. Right? I want a rendezvous to occur, and I want data to be provided by both sources at the same time. Okay? And by the way, that's going to have an effect on their flow of control. Okay? Because it's going to synchronize two components that didn't even know they were communicating. Okay? But that's a choice. Another choice would be a data flow style, which is that this component doesn't have a thread of control at all, but rather maybe it has firing rules. It asserts, say at startup, it says, if my inputs satisfy this pattern, fire me. Then when the inputs satisfy that pattern, it gets fired, and then it asserts a new firing rule. If my inputs next satisfy this other input pattern, fire me again. Right? That would be a data flow style. And now, instead of having a thread of control associated with this, it's a sequence of firings. These are choices, right? There's other choices. So, for example, the inputs might be time-stamped. Okay, so they could semantically carry a timestamp, and I could insist that the components react to inputs in chronological order. So it's given an event with a certain timestamp. It reacts to events with earlier timestamps always before it reacts to events with later timestamps. Another choice. Okay, there's lots of choices for semantic models for component interactions here. Okay, and I think those choices are part of what makes this an interesting way to think about software. By the way, this is not new. Okay, in fact, the first actor-oriented programming language that I've been able to identify was created by Burt Sutherland. There's a picture of him right here. By the way, he looks exactly the same today as he did in 1966. I don't know how he does it, but you know, he really does. But he is actually the older brother of the much more famous Ivan Sutherland. Ivan Sutherland is credited with being one of the fathers of object-oriented design. He created this system called Sketchpad. And Sketchpad was a graphical programming environment that pioneered a lot of the concepts of object-oriented design. Burt, who was the older brother, used Sketchpad to create an actor-oriented programming model. And this is actually a snapshot of something that was displayed on that screen. This is a World War II surplus radar screen that was converted for use with this TX2 computer at Lincoln Labs. This is a light pen, right? This was years before the mouse. Okay, so this light pen would be used to actually draw these programs, and this is in the process of construction. But this program is going to implement Newton's method for calculating a square root. Okay, and it's very much an actor-oriented design for that program. Yeah.
So, for example, on the previous slide, what stops actor from invoking services of class, for example?
Protocol. So right now, if you implement actors in an object-oriented language, you can completely circumvent the actor-oriented architecture and do procedure calls on arbitrary objects. Okay, so don't do that. Right? I mean, this is partly why this question begs a language design question. If you do this style of design in today's languages, the language doesn't help you. It doesn't necessarily hurt you, but it doesn't help you, right? It doesn't help to enforce the design style that's going to lead to an understandable design. So it suggests that there's interesting work to be done in language design where you can come up with languages that would help you. Okay, and I'll suggest what some of those might look like. In fact, I rather like exploring visual syntaxes for such languages because it gets us out of the mindset of conventional programs and into a different way of thinking about programs. But, let me point out that, this is 1966, but there's a whole bunch of things that are out there currently that are clearly fall into this actor-oriented component architecture view of the world. Most of them are domain-specific, right? Programs like LabVIEW from National Instruments or Simulink from the MathWorks. Various programs that are used for hardware design, VHDL and Verilog, are very much actor-oriented programming languages. There's various others, some of them even a bit in more mainstream software engineering. So Corba's event service, for example, is a very much actor-oriented view of distributed objects. The semantics of these differ considerably, so there's quite a richness of semantic models available here. But they all fall into this category where a program is in fact something that is reacting to evolving input rather than fixed input. Okay? So let's go back to the observer pattern. How would you implement the observer pattern using an actor-oriented model? So here's an implementation of the observer pattern in Ptolemy 2 using the rendezvous style, which is a CSP, an implementation of CSP. Okay? So how does this work? Well, each of these boxes here is an actor. Okay? And behind that actor is an ordinary piece of Java code, which is a sequential, non-threaded piece of Java code. It happens to execute in its own thread, but that's not visible to the programmer. Okay? It's just a piece of Java code that executes sequentially. When this value producer goes to produce an output, okay, this annotation on the diagram asserts that the semantics of that production, that sending of a message, is rendezvous, meaning that the thread associated with this guy must be ready to receive that message. Okay? If it isn't ready to receive that message, this value producer will stall until it is ready to receive the message. Okay? So the value producer will rendezvous with the merge, which, by the way, will simultaneously be trying to rendezvous with the value consumer and the observer. Okay? So the value producer is actually, in this implementation, is prevented from producing its output until both the value consumer and the observer are ready to read that output. And then the transaction occurs as one atomic step. The value producer produces the data, the consumer reads it, and the observer reads it simultaneously. Okay? That is implemented. Now, I want to point out that this stylistically is quite different. It's quite a different architecture from the previous one, because the observer now is not really an object now. It actually has its own autonomous thread of control. Okay? So it's not that we're reaching into the observer's brain and changing its state. Okay? We're just presenting a stimulus to it, and it's observing that stimulus. Much better analogy to the physical world. Okay? Moreover, this program clearly doesn't deadlock. Okay? I don't even need a theorem prover to prove this. Okay? There's no feedback loops in it. The only way to get feedback loops in this rendezvous style of communication, the only way to get deadlock is with feedback loops in this particular. That's actually not quite true, but this is actually stronger. Not only are there no feedback loops, there's no loops at all, directed or undirected. Okay? It's a totally tree-structured, well, not quite tree-structured, but it's completely acyclic. There's no cycles directed or undirected in this graph, and there's no way to achieve deadlock in such a program.
But Edward, I think the comparison with the previous Java code is somewhat misleading.
Mm-hmm.
Because in that Java code, you made the comment that you're calling out into some piece of code, God knows where, right? Presumably, this thing is going to be part of some piece of code that will be around it. And when you put this in there, there might very well be cycles.
Absolutely. So you need to be able to do some sort of holistic analysis on the program. But I do want to point out that this is still just as arbitrary in the sense that I've made no assertions about what the observer is going to do with the data that I give it. Okay. This observer is just an arbitrary piece of Java code. It can go off and do whatever it wants. Okay. So in that sense, the design is similar. Okay. So my point is that we've taken a trivial design pattern and we've made it trivial to implement. Well, that's good, okay. But that also actually opens up some more interesting questions that we never would have gotten to with the Java implementation. So for example, suppose that the observer here is lazy, right? And it doesn't get around to reading its input very often, okay? That will have the unfortunate consequence of blocking the value producers and the value consumers if you use this rendezvous style of communication. So you might not want to use the rendezvous style of communication. You might want to use an asynchronous message passing style. So all we have to do is take the same design and replace this annotation with a process network director, and the semantics of this program now is different. So now the semantics is that the value producer can produce data whenever it wants. And it's non-blocking. It just sends data, doesn't care, and goes on doing its thing. Doesn't care if anybody's listening. Who cares? Okay? Here I have a non-deterministic merge, which simply takes streams of input data and arbitrarily merges them. Okay? By the way, notice an explicit, overt introduction of non-determinism exactly where it's needed. Not throughout the program, just where it's needed, which is merging the streams of data produced by these two value producers. Okay? The value consumer, whenever it gets around to it, will read data. If there isn't any data to read, it simply blocks. There's nothing to read, so it doesn't have anything to do. Similarly, the observer will get around to reading data whenever it gets around to reading data. Now, this raises some interesting questions, right? This means that if the value producer can produce data arbitrarily fast, and it doesn't care whether there's any listeners, aren't you going to get buffer overflows? Well, we know how to solve that problem. Okay? In fact, it was solved in Unix pipes. Okay? You need throttling mechanisms. They don't change the semantics here, right? They're just implementation optimizations that keep buffers bounded. Okay? But they don't change the semantics of the program. So the issue is now is that because I've made this trivial design pattern trivial, I can actually now start to ask more interesting questions about the design and elaborate it. Suppose we want to go further and we want to explicitly specify the timing of the producers. Well, now I could use, instead of the process network or the rendezvous director, I could use a discrete event director. Okay, it's another director that we've got in Ptolemy 2. That gives the diagram yet another semantics. Okay? Now every message communicated between actors is time-stamped, and messages are handled in chronological order. So the timestamp is simply a double precision floating point number, happens to be what we chose, okay? And they're dealt with in order. If you have two timestamps that are simultaneous, they're presented simultaneously to the destination, and we guarantee that, okay? So now I can create an actor here that simply produces time-stamped events, which controls precisely when this value producer produces data, okay? And similarly, another one that produces time-stamped events, controlling when this guy produces data. Interestingly, the merge now becomes deterministic. This is no longer a non-deterministic merge because the inputs are time-stamped, okay? So there's semantic information in them about what order they should come out in on the output, okay? So this program has no non-determinism in it. My point here actually is that this is a program, okay? But it's actually a program in a language that is significantly different from Java or C#. In fact, properly I would view this as a coordination language because the functionality of these actors I specify using ordinary Java, okay? But what this program is doing is simply orchestrating the actions of those chunks of Java code, coordinating the actions of those chunks of Java code. Right? So I view this as a coordination language that functions in an orthogonal way to the programming language Java. Okay? They work in a complementary fashion. As I pointed out, the composition semantics is simply function composition. Okay, I think that actor-oriented designs will address this problem of component technologies. There's lots of open questions, right? Do we want process network semantics? Do we want rendezvous? Do we want discrete event semantics? Those are all open questions, right? And it may be that the answers are domain specific for certain circumstances. If you're doing user interface design, you might want a certain style of actor interactions. If you're doing embedded system design, you might want a different style of actor interactions. It's very possible that the answers are domain specific. But I think that there are answers there. What about the question about that this is not what mainstream programming languages do? Well, I think we should just leave that one alone. I think it's really okay to solve this problem at the component architecture level and leave the programming languages alone. Okay. So we can do almost nothing there. Now, there's challenges, right? Computation is deeply rooted in the sequential paradigm, all right? Threads appear to adhere to this paradigm, which is, I think, what makes them appealing to programmers. But in fact, they throw out the essential attractiveness of the sequential paradigm, which is this ability to compose software components in a clean way. Programmers are certainly reluctant to accept new syntax. That's a problem. We all know that. But I think we've actually broken the ice on this, because even Java and C# programmers fairly commonly these days actually use multiple syntaxes. They use UML, for example, together with Java or C#, okay, serving complementary purposes. One is describing gross architecture, the other one is describing detailed implementation. These languages are complementary to one another. I think the coordination languages that I described could function in a similar way. Complementary syntax is describing complementary properties of programs. Third problem is that only languages that are viewed as general purpose get attention. Among language designers, you often, the first question they ask you is, oh, did you write the compiler for the language in that language? And if you say no, they just dismiss you and walk out of the room. And I think that's probably an appropriate litmus test if you're interested in languages for writing compilers, right? But if you're interested in writing languages for designing user interfaces, do you care how easy it is to write a compiler? Maybe not, okay? So I think we should be willing to accept domain specificity in the languages. So the opportunities are, I think that new syntaxes can be accepted when their purpose is orthogonal to that of established languages. The thing that programmers are not going to accept is you're walking in the room and saying, no, I want you to write arithmetic expressions in this new way, right? I want you to use reverse Polish notation to do all your calculations, right? When you want to add the numbers 1 and 2, you should say 1, 2, plus. Oh, get out of here, Who needs that, right? We don't need new ways to write arithmetic expressions, okay? We need new ways to do things that are hard to do in existing languages. And I think coordination languages actually offer a way to do that, because the syntax can be noticeably distinct from the programming languages, and the function that the coordination languages provide is noticeably orthogonal to that of what the programming languages themselves do. So in summary, I think my solution is, I think actor-oriented component architectures implemented in coordination languages that complement rather than replace existing languages. And I think there's a lot of very good research questions about what is a good design of these coordination languages. There's a lot of work to be done on this, okay? I point you to the Ptolemy Project webpage for a lot of explorations into this. We've built actually probably at this point 24 different coordination languages with different semantics within the context of this project, all of them with visual syntaxes. So I'll stop there and give you a list of conclusions. Transformation of bits is the foundation of computation. Threads are the foundation of concurrent programming practice. The foundations are flawed, okay? Concurrent computation needs new foundations. I think actor-oriented component models offer new foundations. And I think that there's a lot of work to be done still on the language design front and certainly on the implementation design front, but I think there's a lot of promise. Here's a few key references. Thank you very much.